I had a cool idea, and the idea is that we would solve a physics problem. Since you're watching this video, I'm guessing you have the same idea. What we're going to be looking at here is a ball that is spinning on the end of a string. Now, when you think about it, physically speaking, say that you take a ball that's dangling off a string and you start spinning it in the air. It does not stay hanging straight down. Neither does it immediately go horizontal. What does happen is that you get a situation where you can think of a vertical line. Maybe it's your hand that you're using this for, or maybe you're spinning it off some kind of post or like a rod stuck in the ground. And then what does happen is that the ball travels on the end of this thing over here. So what I'm saying is, if the ball has this certain mass, this 0.2 kilogram mass, and if it's at the end of a 1.2 meter string, and it also makes a 75-degree angle off vertical, I'm saying that that must be enough for us to figure out what the ball's speed is. Because after all, as it goes faster and faster, it will make a larger and larger angle with vertical. And so there must be just one speed that causes it to travel at this angle. That's what we're hunting for. So in this diagram, we've got a 75-degree angle right here, and the ball is traveling in a circle like this. It is a horizontal circle. First of all, I want to call attention to the fact that the ball is not traveling in a circle with a radius of 1.2 meters. So what is the radius of the actual path? Because if we're going to be analyzing this from a rotational dynamics point of view, we're going to have to know the radius of the actual path so that we can do things like centripetal acceleration. Well, I'm going to look at the motion of the ball from the perspective of a right triangle. If this is a 75-degree angle, I know that this length is 1.2 meters because that's what this is along here. But the actual radius of the circle the ball is moving in for real will be this down here, not the one that goes diagonally, but just the one that goes horizontally. So I'm going to set up a trig relationship in order to solve for that. I'm going to call that x for now. And I'll say from the 75-degree angle, I know the opposite, and I also know the hypotenuse. Think about it. SOHCAHTOA, what are the sides of the triangle that involve the, what trig ratio involves the opposite and the hypotenuse? It's sine. So sine of 75 degrees is going to be equal to the opposite divided by the hypotenuse. So this x will be equal to 1.2 sine 75 degrees. Now, just grab your calculator. And 1.2 sine 75, make sure you are in degrees, is 1.16. It's just slightly different from the original radius, the original length of the string. So the real length of this path is 1.16 meters. I'm going to call that RC. RC because, you know, C means centripetal. So that's the actual radius of the path that it really moves in a real circle. So this whole problem is going to consist of taking steps toward understanding, like, you know, how is the ball moving? How does it affect the answer to the question? The next thing that I want to do is look at the fact that the ball is not moving up or moving down. Because the ball is not moving up or moving down, it must have balanced vertical forces. So check this out. Because there's no vertical motion, you must have balanced vertical forces. There's no way around it. Remember that if there is an imbalance in force, that is what produces a net force, and that produces motion. So because the ball is moving in a horizontal circle. It's not going up, it's not going down, it's staying at the same level, vertically speaking. Whatever force acts on it down, gravity, must be balanced out by another force that acts upward on it. We're going to look at how large that force has to be and also its source. So here is how we're going to analyze that. Think about what must be exerting a force on the ball in the first place. The ball is at the end of a string. Actually, I'm going to do dashed lines here because they're not really physically present. Forces must be supplied by something. Gravity is one force that's kind of unique. It can act without like touching something, but for most forces, you need actual physical contact. The only thing in physical contact with the ball is the string. So if the ball is going to be held in like equilibrium between gravity and some other force, that other force must be supplied by the string. So I'm going to label the tension in the string with Ft. And then for vertical components, I'll say Fty, and horizontal component, I'll say Ftx. Y for vertical, X for horizontal, just like in math class. With this in mind, the force on the ball is equal to mg downwards. This is the gravitational force. It's always mg. The force upwards on it is simply this force, Fty. But wait a minute, didn't we just say that because the ball is not moving vertically, it must be held in equilibrium by equal vertical forces? So really, Fty is also equal to mg. Okay, so this is my next thing that I'm going to like make some progress with. This has to have Fty equal to mg. I'm going to keep track of that over here. All right, so now I would like to be able to write an equation that actually uses the quantity we're after, because what we're going for is the speed of the ball, right? Well, so far we haven't actually written anything involving that. But if you remember anything about circular dynamics, rotational dynamics, velocity, speed, is involved in the statement of centripetal acceleration. So here's where we're going to actually get the first chance to write the quantity that we're interested in. The general formula for rotational dynamics is that the net centripetal force must be equal to mass times centripetal acceleration. This is true in general. This is just Newton's second law, that the net force is always equal to mass times acceleration. And in rotational dynamics, you just put a centripetal on both of those. And you get the nice bonus of having an alternate expression for centripetal acceleration. It's v squared over r. So because AC is v squared over r, you get to say that net centripetal force equals mv squared over r. We're going to look at this the same way that we did for simple dynamics, for linear dynamics. We're going to count up the forces to fill in the left-hand side of the equation. So that's going to be like count up the actual forces in the diagram, and then we're going to set them equal to the thing that we know they must be equal to. All right. Count up the forces. Well, the plural there is a little bit of a lie, because really we know that there must be just one force that causes the circular motion. There's only one thing that's capable of doing it, because there's one thing in contact with the ball. Gravity keeps it from moving up, but it is the horizontal component of the tension in the string that causes the circular motion of the ball. So this becomes Ftx. That must be the net force, the net centripetal force, because it is the only force present. That must be equal to mv squared over r. Well, the thing is, we don't have an expression for Ftx, do we? Yet. Here's what we're going to do. I'm doing this on purpose in a sort of like way where you stumble around and you figure stuff out, because that's the way that these usually go. I've run into a point where I do not know how to deal with the fact that I don't have an expression for this. So what I'm going to do is form a relationship between these two quantities based on the triangle that I had before. I'll redraw it. It's a 75-degree right triangle. FT is along here. FTY is here. And FTX is here. Well, I know that FTY is mg, right? So wait a minute. Now I want to form a relationship between FTY and FTX. And if you really ate your trigonometric Wheaties this morning, then you'll know that I'm looking for tangent of 75, because the tangent of 75 will use the opposite and it will use the adjacent. So the equation I'm looking for here is tan 75 equals FTX over FTY. But I don't need to write FTY. I know that that's equal to mg. So in fact, I'm just going to scrap that. And I'll write FTX over mg from the start. And then FTX equals mg times tan 75. OMG, right? Because now we have something to swap in for this. So I'm going to go ahead and do that. I'll say now mg tan 75 equals mv squared over r. And here I have something that very nicely programs in all the stuff that I actually have in the problem. I have the angle, because that's taken care of by the 75 degrees. I have the r, and I'm going to doctor this just a little bit, RC right there, because after all, RC is really the radius of the circle that we're actually traveling in, right? So the RC is the 1.16 meters that we had before. So let me see. I just need to algebraically isolate the velocity here. And, oh, wait, one more thing. My favorite thing that happens in physics problems is that mass, like so often, doesn't end up mattering, because mass is on both sides, and that means that you can cancel it. Kiss your mass goodbye, right? So now we have to solve for v, the velocity. I'm going to do a couple algebraic steps at the same time. I know that v, when I isolate the v, it must be because I multiplied by RC, and also I must have taken a square root. So I'm going to say that'll be equal to RC times G times tan 75. Take a great big square root of that. And that is, I guess I'll write the numbers, 1.16 times 9.8 times tangent of 75 degrees. And yes, save me, Mr. Calculator. Square root of 1.16 times 9.8 times tangent of 75 degrees is everybody's favorite number, 6.51 meters per second. So what must its speed be? It must be exactly 6.51 meters per second. And that is how you solve a problem where you're given an angle that something hangs off vertical when it's traveling in a circle, and you need to know how fast it's traveling.